ಸ್ಲೈಡ್ ಶೋ ಪೂರ ಸ್ಕ್ರೀನ್ ಬಂದ್ಬಿಡ್ತದೆ ಅವರಿಗೆ ನಮ್ದು ಕಾಣೋದಿಲ್ಲ ಅದಕ್ಕೆ ಅವ್ರು ಏನ್ ಮಾಡ್ತಾರೋ ಹಿಂಗೆ ಇಡ್ತಾರೆ. Baurav, start from the beginning.
Myself, Bagi. My project mates are Laxmi, shirasangi, Rajeshwari Kopp, Vishalaxi, Pujari, under the guidance of Professor Raju Hebbale. My project title, 12-bit high-speed segmented current steering DAC. A 45 nanometer CMOS technology. Design procedure. CMOS 45 technology characteristics. MOS ID versus VD. Curves, basic DAC technology. Using the optimal segmentation, design of unit current cell, design of binary to thermometer decoder, design DAC switches, top level complete DAC.
Baurav and Tim,
Sir.
You can turn off the display so that whatever the bandwidth is there, that can be fully utilized for your PPT. Camera. There is one button. Can you see here? Display. Turn off camera.
Sir.
All of you turn it off. So more amount of network will be available that you can use it for the presentation.
Okay, sir.
Laxmi, mute your video.
Can I start?
Yes, continue.
CMOS technology, 45 nanometer CMOS technology. CMOS means complementary metal oxide semiconductor, also known as the complementary symmetric metal oxide semiconductor. It is a type of metal oxide semiconductor field effect transistor fabrication process. CMOS technology used for the constructing the integrated circuit chips. Characteristics of the CMOS. CMOS devices are noise immunity and low static power consumption. Top level DAC, where an IDC is required to generate the digital inputs for a DAC to make it operate. Digital inputs of 12 bit is passed to the DAC with a clock frequency of 1 gigahertz. It requires also supply voltage. And current steering DAC is prepared the architecture for high bandwidth converts. It works by summing the current producing by an array of current sources. The load of registry is connected to output of the current sources. The high resolution converts of greater than 12 bits have been implemented. Also, a 12-bit design was chosen to balance a resolution and achieving the high bandwidth. To such DACs are used to segment the bits. First 4 LSBs B0, B1 and B2 and B3 are sent to the binary weighted sub DAC. MSBs B4 to B11 are converted using thermometer decoder sub DAC. The output of the local decoder is sent to the buffer and which drives the current switches. The output of the currents are converted into voltage through the load resistor. The dummy buffer is placed between the input binary and binary weighted current cells. Some delays are happen here. LSB cells and thermometer decoder cells. An ideal 12-bit ADC is used to convert the analog to digital signal. Input range of the ADC can be considered as the range of the analog voltages that ADC is able to convert the equivalent digital signal. Input ADC is 10 megahertz. The binary thermometer decoder provides the 4-bit binary code and 8-bit thermometer code. And also binary weighted code is given to the non-overlapping consists of two signals called 1 and 2 alternative being on off. The signals are generated non-overlapping that are never both at the same time. Obtained signal is given to the buffer. The output from the buffer is given to the LSB bank. Also, thermometer code is passed to the MSB bank through the buffer circuit. Output of the LSB and MSB bank is given to the current E, which is converted into voltage, and DAC output will get. Further, will explain Laxmi.
Next to that is so next to that is NMOS schematics. This is the first device which we have designed in the current tool. This uses why we have designed because the working is need to be identified by using this NMOS schematic. We have used this by using a DC voltage of 1.8 volts, and this is the so next to that is hello.
Continue, Laxmi. Don't wait for anything.
Slide variation.
That tell to the Rajeshwari.
Rajeshwari.
What Lakshmi?
Next to slide, please.
Okay.
And this is the ID versus VDS characteristics of the NMOS channel. Then comes the current reference generator. Current reference generator is used because it is used to maintain the constant current across each transistor to generate the 2 microampere per transistor. Next. Here this block generates the bias voltage for the main current source cells in the current steering DAC. This aim is to generate a 2 microampere of the unit current. The current generated is based on the value of the resistor that we have used at the last. Here we have used 14.4 K of resistor. Next will be explained by the Vishalaxi Pujari sir.
Hello, sir. Good morning. Next topic is schematic of unit cell. This is the schematic of unit cell. This is the cascade current cell, which is used to increase the output impedance of the cell. And this is also PMOS current source. And bias voltages are VBP and VCP. These are generated from the reference current. as mentioned in that current reference generator. And this unit current is aimed to generate 2 microampere currents. And next is segmented current steering DAC. This is the block diagram of segmented current steering DAC. And this DAC is divided into 2 sub DACs. One is MSBs and another is LSBs. This segmented DAC is based on current steering technique with 3 bits of binary weighted architecture and 9 bits of thermometer coded architecture. This 12-bit high-speed current segmented current steering DAC is made up of 9-bit thermometer decoded architecture and 3-bit binary weighted DAC. In that 3-bit binary weighted DAC block diagrams. Next, further will be continued by Rajeshwari Kopp.
Sir, myself Rajeshwari Kopp. Now I will explain about the thermometer decoded architecture which we have used in our cadence tool for the designing of the DAC. This thermometer decoded architecture, it mainly helps to convert the binary inputs to thermometer code outputs. In this, I reference is multiplied by the power of 2 because to create the large current. And this decoder is thermometer decoder is purely digital in nature. And here we have employed behavioral Verilog A code for the functioning of the thermometer decoder. It converts the binary input which we have given into the thermometer output. This architecture uses this architecture we have used because it consumes small area, hence it is highly recommendable. And now the advantages of the DAC, that is 12-bit high segmented current steering DAC which we have designed, is it decreases the area and increases the overall speed because we have used a small number of unit current cells, and overall speed will be also increased, and high linearity will be produced as the unit current cells are joined accordingly. And thermometer decoder is used for the MSBs, and binary weighted is used for the LSBs. This binary weighted architecture is so simple and fast, hence it is very easy to use. And this architecture gives the most optimized results, and it gives the accurate speed, and also it is of low cost and also high resolution. And the DAC which we have designed, it uses the less power and highly accurate in nature. Hence this DAC which we have designed in the cadence tool is highly advantageous. By this I will conclude my presentation, sir. Thank you, sir.
Okay, now you show the output of your project.
Sir, as it is only can be done through cadence tool, it is not there in
Okay. Okay. Whatever the last work you have done on the cadence, do you have any proof of that one?
Yes, sir. In the PPT we have added, sir, here.
So go to that.
Schematic of unit cell, and also we have done this current reference generator in the cadence tool in our college, sir. And also this.
We did up to non-overlapping, sir.
Okay, you show from the first this one work. Okay, this one. NMOS schematic. Can you maximize that?
Okay.
You click on the slideshow, Rajeshwari.
Sir, now is it okay, sir?
You click on the slideshow.
Or click on zoom. Zoom option is available, no? Zoom. See at the bottom left corner, the bottom right corner, bottom right corner, zoom option is available.
Okay.
Zoom
Okay, sir.
100% or something is there, no? Just one slider is available at the right
now
bottom
you
corner.
tell me, sir.
You, Rajeshwari,
Yes, sir.
you move that page a little bit left side so that we can see it clearly.
Okay, sir.
The whole picture should be visible to us. Okay, what is this?
NMOS schematic.
NMOS schematic. How you have done it?
Sir, now it covers the whole.
Yes. Now it is visible. No problem. This is NMOS schematic. What you have done in this one?
Okay.
Bauravvan, Rajeshwari, Laxmi, and Vishalaxi.
So to check ID versus
We have used
VDS
the
characteristics, we have designed this NMOS schematics. Sir.
Okay. From that, what did you understand? What did you understand by this? You tell me.
Sir, for the basic building blocks of the current reference generator, NMOS 2 volt is required for the operation, sir. So first we have to check whether it is working or not. So that's why we have designed for this purpose.
Okay. After doing this one, you have drawn the graph of ID versus VDS, no?
Yes, sir.
Yes, sir.
Go to that slide.
Okay, sir.
Okay. What do you understand by this graph?
VG.
Can anybody tell what is this graph?
Sir, it is drawn versus ID, that is drain current, and VDS, that is drain to source voltage, sir. Keeping the IG, that is ground current, that is it is constant, sir. The plot will be like this, sir.
IG you are keeping constant.
Yes, sir. IG is
Bauravvan,
equal to.
Yes, sir.
what are the three parameters you are
VGS.
considering to plot this graph?
VG is equal to 0, sir.
But
And
Rajeshwari is
ID and
telling
VDS is.
But Rajeshwari is telling IG has to be kept constant. Is it correct?
Sir, VGS is equal to IG into current into time, sir. As IG is 0, VG is also will be 0 only, sir.
Rajeshwari,
Yes, sir.
do you think that from the current there will be a voltage or from the voltage there will be a current?
From the voltage there will be current, sir. VGS will be 0, sir.
Better you take admission to the third semester again. Will you do it? Rajeshwari, you take admission the third semester, study voltage current, then when you come to the 8th semester, again give the project. Because of voltage, there will be current, no?
Yes, sir. Because of voltage there will be current, sir.
What you have to tell? You have to tell VGS.
Yes,
What about Laxmi and Vishalaxi? What is your answer for this curve?
VGS is equal to 0, then only IG equal to 0.
VGS is equal to 0. Then what you are doing? One value you are getting, one curve. In the graph, there are how many curves? 1, 2, 3, 4, 5, 6 curves have come, no?
Yes, sir.
For which values of voltage or current, these 6 curves you are getting? Whether the NMOS you have designed, is it enhancement type NMOS or depletion type NMOS?
Enhancement of NMOS.
Enhancement of NMOS. Yes? Bauravvan, Rajeshwari, Laxmi, and Vishalaxi, all you have to tell.
Yes, sir.
Is it enhancement type NMOS or depletion type NMOS?
Enhancement type.
Are you sure?
Yes, sir.
How do you say it is enhancement? I say it is a depletion. How do you classify the NMOS between the enhancement and depletion? How do you say that it is the enhancement type? Why not it is the depletion type? I am not getting answer from anybody. It means that you people don't know what is the difference between enhancement NMOS and depletion type NMOS. Correct? Baurava, Rajeshwari, Laxmi and Vishalaxi. If you don't know the answer, at least tell me that we don't know. So I can ask you the next question. Don't know? Am I audible to all of you?
Yes, sir.
Yes, sir.
I said you, if you know, tell. If you don't know, tell me that we don't know the answer, sir. So that I continue with the next question. Don't know? Each one of you have to say. Okay. Such how many NMOS you have constructed in your project? Go to the slide number 7.
Okay, sir.
So here you have used NMOS, no?
Sir.
Yes, sir.
How many NMOS you have used in this diagram?
6 NMOS, sir, and 6 PMOS.
Whoever is speaking, speak loudly so that we can hear your voice.
6 NMOS transistor and 6 PMOS, sir.
6 NMOS and 6 PMOS. Yes?
Yes, sir.
Yes, sir.
In the slide number 5, you had an NMOS schematic, no? Like that, do you have PMOS schematic?
Yes, sir. But here.
Where you people have not shown that. Only NMOS schematic you have shown. PMOS schematic is not necessary.
We didn't get the proper output, so we didn't.
You didn't get the proper output of PMOS schematic. Then how did you implement this using 6 NMOS and 6 PMOS? Why you people didn't get the output of that PMOS? Why did you did not get the output for the PMOS schematic? Baurava, Rajeshwari, Laxmi and Vishalaxi, you people have to speak. Otherwise, I will disqualify your batch. I have been telling you people that if you know, tell me. If not, at least tell we don't know. Don't waste my time as well as sir's time. We have other batches to conduct.
We have did sir PMOS schematic, but we have not included in this PPT, sir.
Why you people have not included, whether it is not there in your project?
No, sir, it is there, but we didn't took a screenshot of that, sir.
Then what you people have done? Can you show me can you have the output of this diagram, whatever you are showing in the slide number 7, saying that, sir, this is the input we are giving to this circuit and this is the output we are getting, and this output we are getting because of these are the things that are happening in between in the system. Like, can you show that diagram and tell me? What is the input and output of this figure, whole figure? You have written it as current reference generator, no?
Yes, sir.
What is the output of this whole figure?
2 microampere current.
Current will
Current.
vary, sir.
Current will vary in the sense from what value to what value it will vary. What is the range of current variation?
Up to 2 microampere.
From 0 to 2 microampere.
Yes, sir.
When the current will be 2 microampere? When do you say that the current is 2 microampere?
Input.
What is the input you are giving to this whole circuit?
Voltage, sir.
Voltage. What voltage you are giving? Analog
Volts,
voltage,
sir.
digital voltage. What is the range of voltage? Whether you vary the voltage? How much?
2 volt.
2 volt. 2 volt you are giving to what? NMOS or PMOS?
Both.
Are you sure that you are giving 2 volt?
Register value, we given the input as the register, sir.
Who is this? Laxmi or Bauravvan?
Borrowers, when we vary the input, then register value also change.
Why do you want to change the register value? Whether you have used any register here in this diagram?
Yes, sir.
Where? Can you show that?
At last,
These are only NMOS and PMOS. These are NMOS and PMOS, no?
Sir, last year there's, sir, one register.
Okay, leave about that register. Apart from that, you see so many NMOS and PMOS transistors you are using, and only one register you have used, and you are talking about that register. You tell me the working of this whole. For example, where you are giving input? From here, VCC. Yes or no?
Yes, sir.
These two things are the what output?
No, sir.
See, you have indicated two red arrows here, right? On the right side of this image. Whether those two are outputs? Whether those two are outputs? It means you are getting two outputs from this. It means you are getting two outputs from this part. Bauravvan, Rajeshwari, Laxmi, and Vishalaxi.
Yes, sir.
Your knowledge about your project is very, very low. In fact, it is zero. We are not happy with your presentation and the knowledge, whatever you are demonstrating through the project. We are totally unhappy with your performance. Now you can leave the meeting. We'll take up the next batch. You can leave the meeting.